Refraction from rarer to denser medium at a convex spherical refracting surface. We know that convex spherical refracting surface is a converging refracting surface and it can form real as well as virtual image. So now to start with, now this is pole P and sign conventions that we take is all the distances measured in the direction of incidence light. Incidence light means in this direction are taken to be positive and in the direction opposite to the incidence light is taken to be negative. That is, in this case, about this axis that is taken to be negative. Similarly, the heights of the objects which are measured above the principal axis are taken to be positive and below that is taken to be negative. Now to study about the refraction from rarer to denser medium at convex spherical refracting surface or any spherical refracting surface, some assumptions are to be taken that the object which we are taking, for which we are observing the refraction, should be the point object. Right, that should be very small in size and that should lie on the principal axis. And second assumption that is need to take the angle which are made by these incident ray to the normal are these very smaller angles such that sine of angle incidence I, that is sine I will be equal to I and sine R will be equal to R only, considering that these angles are very small. Now you can see the diagram here. The object O is lying at point O and is incident at angle I at point A with the normal. This line is the normal which is drawn from the center of curvature to this surface. Okay, and since the light is going from rarer to denser medium, so it will bend toward the normal, making an angle beta. Here I is known as the real image of the object O. Now we draw the perpendicular to the principal axis. This OI and extended is known as principal axis, which is passing from the pole. Okay, so AM is the perpendicular drawn on the surface, and the next assumption is first assumption was the point object should lie on the principal axis, angle should be small, and third assumption is the aperture should be small. Okay, so in that case, if aperture is small, this point M is lying close to P, so we will replace M by P. Okay, now to start with, what are the angles? Angle this is AOA and let this is angle N. AOAN angle is equal to angle I. Okay, and angle AIM is equal to beta. Angle AIM is equal to beta. Angle AOM is equal to alpha. Angle AOM is equal to alpha. Angle ACM is equal to gamma. Angle ACM is equal to gamma. Okay, now we can apply the rule that sum of internal angles. Second step to be followed is the sum of internal angles is equal to the external angle. Now in this triangle AIC, you can see that internal angles are R and beta and external angle is gamma. So gamma is equal to R plus beta, and from here we can find the value of R, which is equal to gamma minus beta. Let me give it number 1. Similarly, in this triangle OAM, angle alpha, OAC, angle alpha and angle gamma is internal angles, and angle I is external angle. So we can write I is equal to alpha plus gamma. This is number 2. Now applying the Snell's rule. According to the Snell's rule, we can have mu1 sine I is equal to mu2 sine R. So accordingly, sine I by sine R is equal to mu2 by mu1, or that is approximately equal to I by R, since we have assumed that the angles are very small, since aperture is small. So accordingly we can write this mu2 R is equal to mu1 I, or mu1 I is equal to mu2 R. Now putting the values of I and R here, mu1 I is alpha plus gamma from this equation, and mu2 is gamma minus beta from this equation. Give it number 2. Now apply the rule theta angle is equal to arc upon radius. Arc upon radius. Right. Now in this case, if we see the diagram, this is angle alpha, and for this the length of the arc is this. If we complete this circle like this, so length of the arc is this and the radius is this. So let we assume there is a arc. Okay, so in that case we can write that alpha is equal to am upon mo. Right. Similarly, beta can be written as am upon mi, and gamma can be written as am upon mc. So putting these values in this expression, we will be having mu1. Alpha was the object distance, object angle, so that will be am by mo, plus gamma was center of curvature, at center of curvature, so am by mc, which is equal to mu2, again gamma is am upon mc, minus beta was at image, so that is am upon mi. Now this all am will be cancelled out, and we are left with this is mo, mc, mc, mi. Now we know that the third assumption that we have taken is aperture is small, so m is lying very close to p. So replacing m by p, in that case we will be having mu1 1 by po plus 1 by pc is equal to mu2 1 by pc minus 1 by pi. Now taking the sign convention, here we can see that po is the distance object, which is taken to be minus u, because it is in a direction opposite to the direction of incidence light, and pi is plus v as it is in the direction of incidence light, and pc is r, which is the radius of curvature, which is also taken to be positive. Now putting all these values in that equation. Okay, so now in this case, this pc term will be taken collectively and this pi will be taken to that side. So we will be having mu1, this is 1 upon po plus mu2 upon pi is equal to this mu2, and this mu1 is taken that side, minus mu1 upon pc. So putting the values, mu1, po was distance object, which is taken to be negative. Pi was the image distance, which is taken to be positive, plus v. So is equal to mu2 minus mu1, and r is taken to be positive. So this is the formula for refraction from rarer to denser medium for the real image at the convex spherical refracting surface.